Oh no. Okay. So for class A, B, and C, those are called as transconductance. Amplifier. Because those amplifier utilize the GM, right? So it is just uh, effective uh, GM is just only a function of just conductance angle, right? So this is let's say this is a 180 degree, and this is a less than, if the reference is higher, then it is less than 180 degree. So this has a so 360 degree, and this is between 180 and 360, and class B is 180, and class C is between 0 to, theoretically it can be 0 line, 0 to 180, less than 180 degree. Okay, so today what we're gonna talk about is the switched power amplifier, which is totally different from those transconductance amplifier. Switched power amplifier utilize a device as a switch, which is just a switch controlled by input voltage, gate voltage. Okay, so therefore, this switch mode power amplifier is naturally, you know, uh, doesn't consider the voltage gain. Okay, so it doesn't have any specific voltage or current gain. Okay, it only has a saturated output power. Okay, because any signal in amplitude is just given by this kind of you know uh, constant magnitude, which is just uh, given by P set. So that is just a 2R multiplied by P set. Okay, it does not change the magnitude. Okay, that's the main difference between uh, transconductance amplifier and this switch mode power amplifier. So we can say this switch mode power amplifier has a relatively large, efficiency. Okay, relatively large efficiency, but it doesn't provide any specific voltage gain, which is a power gain. Okay, that's a quite different concept from the typical transconductance amplifiers, right? So the first class is a class D amplifier. Okay, so this class D amplifier is also modeled like two switches. which is operating in complementary way, which means when this switch on, then this switch off, this switch off, this switch on. Okay, so it's something like charging and discharging. Okay, charging and discharging. So this Class D amplifier is nothing more than just inverter. That's just a basic concept. Okay, once we put certain amount of power, then this switch on, so it charges through this resonance circuit. Since this resonance circuit is operating at omega 0, right? So at other frequency, this is large, which means at output, the harmonic component is suppressed, but uh, you know the fundamental signal is just going throughout this series uh, reactance term. I mean, series resonance circuit. So therefore, it is providing this kind of voltage. Okay. So be notice also be noticed that if you take a look at this point, right? So the output is exactly just a rectangle. Output is exactly rectangle, right? So if it is charging and discharging, so the output is exactly rectangle. So what it can say is that you know the output voltage is a rectangle while the current is a sinusoidal. So which is just looking like this. If you take a look at the VD here, of course, V out is a sinusoidal, okay? So what we are looking at is here, okay? So as you have seen before, this is just if we just, input large enough swing, it doesn't necessarily to be this. If you just put large swing, then for certain amount of reference, it becomes turn on, right? And a certain, reference, it becomes turn off. So it's something like this, effectively. So the output is exactly switching on and off. So when this is switching on, then it is high, and when this is a switch off, then it is low. So the magnitude at this point, which is a drain voltage, is exactly rectangle. Okay, so and also when it comes to current, right, the current has two paths. So when this is a high, which means this is off, and this is on, right? Then the stored current at this charge, I mean, stored current, stored charge at this, capacitor is, I mean, you know, when this is on, this is charged, right? This is charged. So, however, there is no current conduction ID. ID is 0, right? ID is 0 because this is open. So when this is on, and this is off, right? Then the stored charge over here will be discharged through here. Okay, so this is ID, IDT. That means, definitely because of this resonance circuit, its shape must be looking like sinusoidal, right? Sinusoidal. And once it's discharged, or then it started to switch is started to switch it to this way, right? Then it started to recharge, right? So since there is no current conduction pass to here, then you know ID is 0 at this point. So once this is switched on as before, switched on and switched off, then we started to discharge. Okay, so as can be seen in this VD and ID graph, right? There is no power consumption caused by those you know device, because in order for this device to consume the power, right? Then ID multiplied by VD has to be some value. But for this case, when ID is high or ID is larger than 0, then VD is 0. When VD is larger than 0, right, ID is 0. When ID is larger than 0, then VD is 0, right? So either case, there is no overlap between VD and ID. Therefore, this is always 0, which means there is no voltage, no power consumption via the active device, via the switch, which means the efficiency, which is defined as PDC and PD, drain efficiency, right? P out must be 100% because there is no loss caused by this device. Therefore, theoretically, uh, the Class D inverter, which is a Class D power amplifier, is giving 100% of efficiency. Okay, makes sense. However, this is the real case, right? There is no such a switch, right? Because it doesn't have any, intrinsic voltage. Intrinsic resist at all. But this is not the case, definitely. Okay. So definitely it might have a resistor throughout this. Therefore, when this is a conductor, then voltage is not zero. Voltage is non-zero, right? Because this is R off. When this conducts, right, there is a small leakage, right? Also, when this is dissipating, there exists a small amount of R on. Therefore, the voltage VD is ID multiplied by R on, right? So which gives power consumption of this amount, right? So definitely, for switch the power amplifier, the efficiency is determined by the on resistor. Okay. So in order for us to reduce the on resistor, right, we need to make a device size quite large, right? However, if you make this device size quite large, that means we need more power to drive this, output stage. Okay, this is not the free, right? There is no free lunch, right? But also, as can be seen over here, right? The inductor itself is quite lossy, right? So it also consumes power. Okay. So let's take a look at the efficiency of Class A power amplifier. So as we can see, the efficiency is 100% for ideal switch, right? Because ID multiplied by VD is always 0 because of no overlap region, right? So and let's just more take a look at more analytical way. Okay, just VD is just VD is switching, right? Switching. This is VDD, and VD is just because of, this is let's assume it's something like this. Okay, so this is a middle of VDD. Okay, so this register and this register is the same. Okay, so we have a swing of whole swing of VDD, right? We have a whole swing of VDD, which means in the middle it becomes VDD divided by 2. So this VDD divided by 2. Okay, so uh, basically this is something like this, right? This is a sine, right? This is a rectangular pulse. So basically we have a, this is a 0, this is a sine, and it is moving to this value. Therefore, VD is given by this, right? So as can be seen here, right? So if you describe, you know, this rectangular pulse in terms of Fourier series, right? It's looking like this, right? So uh, which is just calculate using, because this is order harmonics. So we just take this only. Let's say this is, if you just say theta and n omega t, and this is an. An is an is pn, right? Pn is what? Pn is just 0 to, this is half, just pi and plus pi to 2 pi and minus 1. Of course, this is VDD over 2, right? VDD over 2, but just consider sine n omega t. Here, n omega t is just a set, okay? And dt, dt, right? So from this, since this is order harmonics, so it only has a sine component and it only has order component, so it is given by this. Okay, so therefore the load current is just VDD divided by 2 multiplied by 4 pi and sine theta. Okay, so and this is a voltage, right? So this is a voltage divided by R is current. So you just just put current over here. So it is 2 VDD by pi R sine theta. Okay, that's why you get this. Okay, once you get IL, which is theta is just omega t. Okay, then the load power is just what? Load power is for the peak I square R divided by 2, right? So from this is IL square. I is what? Pi R to VDD pi R sine theta. right? In r sine theta. So just take a scale and r divided by 2, right? And which is just pi square and 2 VDD scale, right? And r cancel, so this is r, okay? So this is approximately 0.2 VDD scale divided by RL, okay? So this is a load pump. And how about we need to calculate, in order to calculate efficiency, right? Efficiency is PL divided by PDC. So we need to calculate the PDC, right? So PDC is IDC multiplied by VDD, right? Okay. So what is IDC? IDC is just a half sine, right? Half sine. If you just take Fourier series for the half sine, then DC component is IP divided by pi, right? That's very easy to get. Okay, so because for the DC term, right? DC term A0 is T over 2 equal to 2 pi and sine. Since this is a half circle, this is pi and sine theta d theta, right? Therefore, this is a minus cosine theta, and 1 over t is just 2 pi over 2 and pi 0. So pi, if you put pi, right, this is a minus 1. If you put 0, this is 1. 어떻게 이게 저게 안 맞냐? 플러스가 되어야 되는데, 그죠? t분의 2 사인 제곱은 마이너스 코사인이고, 그래, 맞네. 그러니까 0에서 2지, 0에서 파이지, 그지? 플러스 코사인이 하면 1이고 마이너스 1은 플러스 1 하면 2지, 그지? 그럼 파이 오브 2네. 그죠? 이게 t면 EC는 내가 뭘 잘못 계산했지? 왜 E 오버 파이가 나오지? 왜 DC가? 내가 뭐 잘못했냐? 응? 야, A0가 이거 아니야? 하프 사이클이니까 파이고, 그지? 그 다음에 사인 세타에 D 세타. 그지? 가만히 있어. 갑자기 프레 시리즈가 내가 헷갈렸네. 응? Let's take a look. 자. A0가 어떻게 계산? 사인의 dx 맞는데. 아, P분의 1이구나. 아, 이게 헷갈렸다, 이게. 어디 갔지? 갑자기 내가, 어? 갑자기 프레이 시리즈가 헷갈려가지고. 야, 프레이 시리즈가 다 헷갈리냐. 참. 야, 어디 있냐, 이게. Right, so let me just, clarify. The free series, right? Free series is just A0 plus sigma AN cosine n omega t, right? Plus BN sine n omega t, right? So previously we used this, right? So here Bn is 2 over 2 t. So this f t sine n omega t, right? An is actually A0 is An is 2 over t t f t cosine n omega t dt, right? How about A0? That's what I got confused. This is a 1 over t, right? Why you guys didn't say anything? Okay, this, right? So this is correct. 2 pi over 1 and 0 to pi and cosine. Let's say sine theta e theta, right? So which is 1 over 2 pi and cosine theta and 0 to pi, which is 1 over pi. Okay, therefore it's 1 over pi. That is d theta. Okay, 이거 뭐, 너 혼자 아냐 지금? 어? 대답이 없어. 응? 손가락 앞에 죽겠구만. 응? 하냐 안 하냐 너들. 시험 쳐야겠네. 들려?
네.
들었어.
왜 나한테 지적을 안 해? 왜 이게 내 이라고 써놨는데 왜? 아무 소리도 안 하네. 응? 너 시험 쳐 그러면. 뭐 어차피 테이프아웃도 안 하는데 시험 쳐야 공부하지. 겁나도 공부 안 하는 사람들. 응? 나는 힘들어. 그렇지만 공부를 시키려면 어쩔 수 없어. 내가 힘들어야 돼. 그래야 학생이 하지. 응? 알겠지? 그래서 therefore that's why it is IP divided by pi. So here we already calculated the IP, right? So it was 2 VDD divided by pi R L, right? Which was previously, calculated. Therefore, IQ is given by this, right? So if you guys put them together, right? IQ and VD, which is given by this. Look at this. This is exactly the same with the PR. Therefore, efficiency is 100%. Okay? QED, right? So there are so many practical issues in Class A power amplifier. As previously noted, a real Class A amplifier efficiency is reduced, right, due to the switch-on resistance. Right? Therefore, I said we need to increase, the switch size. However, if we increase the switch size, right, that will increase the parasitic capacitance, CGS plus CGD. Those are the main parasitic capacitance, right? So we may say this is 1 plus gamma, right? Here CGD is gamma CGS, okay? CGD, which means CGD is just proportional to CGS. Therefore, we may say this is 1 plus gamma CGS. Okay. So, what is a CGS? CGS is 2 divided by 3. If this is uh, what is that? In the saturation mode, right? 2 divided by 3 and Cox and double of L, right? And if this is operating in triode region, because you have to integrate, right? Because device itself is operating between cutoff, cutoff, and triode and saturation. All of them are just all of them exist in single operation. Right? So it is something like this, moving back and forth, back and forth, back and forth, right? Let's say this is VDD, and let's say this is 0. So, you know, drain, VDS wise, this is moving back and forth, back and forth. Right? So therefore, we cannot say CGS is just a 2 over 3 COX double over L, right? We need to take integration depending on the operation. So, but we may say approximately CGS is COX double L, right? Which means this is this parasitic capacitor is proportional to double and L. So if you increase the size, then this CGS will be increased quite a lot, which means this charging discharging loss, right? 1 over 2 CV square F, right? This is power, right? This power is gigantic because this is quite large. For example, let's say this V is 5 volt and C is 50 femton, and this is 0.5, and this is let's say operating at 2 gigahertz, right? So this is a, let me calculate. Okay. So 0.5 multiplied by 50 to minus 15 multiplied by 5 square multiplied by 2 9, which is 1.25 milliwatt. Okay. This is compared with the output power, right? PL previously was pi scale and R and VDD scale, right? 2, right? So this, right? So let's say this PL is a 50 and pi scale and 2 multiplied by 5 scale. Okay. What is this value? This is a 100. Okay, approximately 100. Okay, so this charging and discharging itself alone give this value. So if you increase device size to reduce, you know, the loss caused by one resistor, if you increase device size by 10 times, right, it's exactly reflected to the loss from the switching loss, right? Loss from the switching. So it becomes a 10.25 milliwatt, which is almost 10%, more than 10% of total power delivered to the load. Okay. Therefore, you guys have to be very careful when you increase device size. Okay. So you have to perform very careful balancing between for the optimum switching size. Okay. Also, we noticed that even though all the power amplifiers are operating in high efficiency regime, it's magnitude in terms of delivered power is quite small. Okay, you guys should understand that. Okay, the reason of using switch mode power amplifier is only for the efficiency, not for the power deliverability. Okay, that's a very important thing. So we noticed that people never ever try to use inverter as a capacity amplifier. Okay, because there is loss caused by uh, the PMOS, right? And also the second issue is you know the swing itself is quite limited, right? Swing itself is quite limited if you take a look at the mechanism of this. So basically, this has a VD set, right? VD set. So this also has a VD set. So the swing itself is limited quite a lot. VDD minus VD set. P, this is a VDD. This is zero. Zero plus VD set N, right? So the swing itself is limited, right? Therefore, the deliverable power is also limited. So in order to avoid those, issue, people use crest amplifier in form of differential. Okay, so it, the structure is given by this. Okay, so the only downside is this, on-chip balloon, which is a little bit lossy, right? But if you use this balloon, right, part of inductance can be just swallowed inside of this, transformer, right? So it's very, nice looking structure. Also, the power level is twice the, right? Power one, power two, combined in voltage mode, right? Therefore, it's driving up power level is improved as well. But more importantly, if you construct a differential structure, right? You know, it has a common rejection, right? So if you just use this single, single-ended structure, then always you got trouble with uh, this inductance, right? This inductance is omega has a omega L of reactance term. So if there exists a current conduction, then this amount of voltage is dropped over here, which will reduce, you know, quite a large amount of voltage swing at output, right? So, however, if you use a differential pair with a, common mode grounded, then you may avoid all of them because this is a virtual ground, right? You don't see any inductance or whatever over here. Effectively, the current is moving back and forth over here in this way. So you may avoid this common mode, issue. More importantly, since this is a differential mode, right? So there is a less amount of signal injection, right, through this uh, common mode. Okay, so this is a quite a serious issue actually. If this is a swing and this impedance is not that good, for example, let's say there exists inductance, then the swing will induce another, you know, the voltage drop over here. And since those are connected together with the other structure, right? So for example, all of them are just connected together, right? This is a VDD. So this, you know, certain amount of, common mode signal will affect on oscillator, which will change center frequency. This is called a VCO pulling. Okay, this is a very serious actually. In old days, when PLL is not that good, this is a really serious problem in communication system. Okay, so if once you just implement a differential, crest amplifier, then this kind of injection is reduced quite a lot, which may, you know, prohibit VCO pulling. That's a really, important uh, thing that you need to understand. Okay, right. So let's take a, more practical analysis. So let's assume high Q tank so that output current is purely sinusoidal. Okay. So I out is just I O sine theta plus pi. Okay. And the voltage at the secondary of a transformer, right? So as you remember, right? So this here is transformer, and there is another transformer over here, piston and resistor. Okay, which is crest amplifier. So the voltage at the secondary of transformer is let's say this is N2, this is 1 to N, 1 to N, right? Okay. So the voltage at the secondary of transformer is scaled up by N times, right? So since this is a sine function, right? It's a sine like this. So uh, the output voltage is N and VDC sine, and also uh, you know the current. Uh, the transformer has its own resistor R on. I mean the device has R on resistor. So what you can see from this side is N scale, R on, and the current conduction is I0 sine theta plus pi. That's why you get this. Okay. So the voltage uh, at the secondary of transformer is given by this, right? So transformer direction is not shown here. So from this line, the fundamental component of secondary load voltage, uh, as we've seen before, right? V load is RLI out. So, uh, you know, this is actually, after this, what is that? Series, resonant network, and this is VL. So this is only, this has only, omega zero term. Okay. So uh, eventually, uh, you know, it has a n scale I out R on term, and this VDC term is just m multiplied by VDC and sine single function, which is 4 over pi term at at first harmonic, which is for the fundamental. This is from the sine. Okay, as you've seen before. Here is a sine. Yeah, this sine. Okay. So therefore, we got VL in this way. You notice that other part, because this is this has this consists of multiple harmonics, right? All of them are just one away from this bandpass filter. Okay, that's our assumption. So VL is given by this. Therefore, it's clear. So voltage and current are in phase. Okay, so we just assume pi is just a 0 for the maximum. If those are in phase, then this becomes the largest. Okay, so from this relation, we can just this is RL I out equal MVDC pi, and let's say this is 1 I minus n square I out R on, and we just rearrange it for IO. Okay, IO, and just RL and plus n square R on I out equal NVDC 4 over pi. Okay, so you can calculate I on equal NVDC and 4 over pi, and just take out RL, and something like this fine. So you get I out. Okay, this is this, right? NVDC. 맞지, 그지? So we get this. Okay. So also we notice that each transistor conductor half sinusoidal pulse, right? Each transistor, because this is a switching complementary way, right? In complementary way, when this on, then this off, right? So which means it is something like this. Okay. So this alone, right? It is something like this. This alone, it is something like this. Okay. So therefore, this I and this I also I are same, right? So which is as we were observed, right? So this is actually 1 over pi. So this is I out, and since this is a 1 to n transformer, so the current I is actually this is wrong. Actually, this has to be n, right? Because we just defined it in this way. In this way. So if I just let this n, this is 1, then IDC here is if I express I out, this must be I out divided by n, right? So it must be this. Okay, something is wrong. Okay, so DC power is VDC multiplied by those, right? Those are from here. So pi RL and 4n VDC multiplied by 2, so it's 8, and 1 plus n square R on RL1,
Môn gì
and
đấy?
so here we have to take n. So actually not this, n is gone away. Okay, I think it's wrong. Okay, so P out is given by this.
Ừ.
So eventually P out minus PDC, right? P out minus PDC. What is a PDC? That we calculated this, right? And the result is the same, right?
Ừ.
We just, neglect this. Uh, but number two, I can, I is 이상하다 이거. i가 여기 있잖아. 왜
Ừ.
이렇게 돼 있지? 이게 잘못돼 있네. 이게 음, so as you can see, right, this is a, as you can see the out, B out, right, you can easily see that R on is scaled up by
Ừ.
n scale, right,
Ừ.
which means this inductor is has a transformation ratio, right, transformation ratio of n to 1, right, because this is R, this R on is reflected
Ừ.
as n times n square times r on, right? Make sense?
Express. Okay.
So that means this ID1 is should be scaled like this way, right? Should be scaled
Ừ.
like this way. So if you put this together, then n 1 over n pi multiplied by pi rl o n vdc and this. So this cancels. Therefore, this pi square RL for VDC, right? Otherwise, the result is looking very weird. Why? Because this power consumption is become a function of n scale. How come this is possible, right? This is impossible. Why? Because this DC is independent of ratio, right? This is just this ratio. How come is this related to this ratio? This is nothing to do with this ratio is nothing to do with the power consumption at this, right? It should be canceled out. So like this, okay. So this is something wrong. So we just okay delete this, and so VDC is 4 multiplied 2 multiplied by what? This is a DC scale, right? DC scale, DC scale, DC scale. Okay, you have to add this scale as well. Okay, right? Okay, so 1/2 of I scale RL is what? Half of I scale is I scale is what? 4n, right? So 16, 16,
60.
and n scale and VD
Ish.
DC scale, right? And this is a pi scale, and this is RL scale.
Hai.
Okay, and so what is RL? RL. I square is this 1 plus this also has to be scaled, right? Right?
예.
이것도 제곱돼야지.
네, 제곱됐다.
어,
I 더.
제곱돼야 돼, 그지? So P out은 어떻게 되냐? So P out is what? Uh, this, right? This divided by PDC, right? PDC is previously this, right? So 8 VDC square pi square RL, right? And this, right? So we cancel out, and this cancel, this cancel, this cancel. 이 R 스퀘어 있냐? RL, 그렇지. 이게 되지. 캔슬, 그지?
네,
맞지?
맞습니다. 네, 맞습니다.
근데 이건 지금 RL만 있잖아, 그지? 요 RL 캔슬이지. 그지?
네.
그러니까 지금, 이거 왜 이래? 사이즈가 어떻게, 갑자기 커졌네, 이게. 어떻게 되지?
음.
잠깐만. 지금 안 되네. 그러면 어떻게 돼? 결국 남은 건 지금 여기 n 스퀘어 남았지? 그지? n 스퀘어에, 그지? 1 플러스 n 스퀘어에 RL,
R, R,
R on,
R, 온.
RL. 이렇게 되지, 그지?
네, 맞습니다.
그지? 여기 n 스퀘어가 빠졌지. 어.
네.
그러면 이거는 make sense 해. 왜냐면, 만약에 이게 이거보다 훨씬 크면, 지금 결국은 efficiency라는 거는 R on에 대한 RL이란 말이야. 그지? 네, 그럼 efficiency가 원트잖아, 원트. 맞지. efficiency가, 만약에 이게 1이면, on 스위치가 0이면 있잖아. 이게 0이면.
영,
이게 0이면 0이지.
1, N죠.
그러면은, 이게 n 제곱이 되나? 이것도 이상하다.
1분 N죠.
그러니까 1분의 n 제곱 이상하잖아. 1이 나와야지, 효율이. 맞지? 이거 이상한데. 아이고. 아이, 맞잖아. 맞아. This is correct. Why? Because you just think about that. I got confused. Okay, this is correct. Why? Because if you take a look at this, right? So I said, right, this is a 1 to n transform, right? Which means current wise, right? This is 1 to n for current. Okay, makes sense. So, for example, let's say this is a V1, right? V2, and this is a 1 to n, right? So, let's say this is a lossless, right? Then voltage is scaled up, so it becomes V1, right? The current has to be scaled down, right? Let's say this is I1, right? Then the I2 must be I1 divided by n. Otherwise, to meet the power conservation, right? Make sense? Since this is a 1 to n, right, transformer, so current-wise, this is a, let's say if this is 1, then it becomes n. So it has to be n. That's correct. Okay, this is correct. Right? So I got confused. Yeah. 시질을 한다. 실수를 하네. 우리의 시리즈도야 막 실수를 하고. Anyway, this is correct, okay? So this makes sense, right? So whenever you derive any equation, right? So you need to check the sanity, right? Each sanity. If it doesn't work based on your common sense, then you have to go back, okay? So let's see, what if R1 is 0, right? This is an ideal switch, right? Then definitely efficiency has to be 1, right? This is true, right? Make sense? Okay, so this is correct, okay? So, but we notice that in order to improve efficiency, there are two ways, right? We need to set this n as small as possible, right? For example, 2 to 1, 3 to 1. Those are good, right? Because since n is smaller than 1, right? Make sense? However, right? However, if you increase the ratio in either side, then it will induce a loss, right? So that's what we already mentioned before, right? However, for the switched amplifier, this is a very important to have a high voltage switching at this node, high voltage switching at this node, and low voltage switching at this node, at this branch. Okay, so that means if you just what if we just implement switch amplifier with a step, right? As I drive you guys to design with a stepped amplifier, right? What if we just step and to make this output voltage large and to make this transformer ratio less than, let's say this is a 2 to 1 or 3 to 1, okay? Then we will improve efficiency based on this equation. We cannot reduce R1 arbitrarily. Why? If you reduce I1, then this size will be increased. That will halt your FT, right? So the switching will not operate properly, right? So also, it requires a large amount of power to drive this output stage, right? So I think a better way to improve efficiency is to step. Of course, R1 will be increased, but still, this is n scale. Okay, so we can reduce the effect quite a lot. For example, let's say R1 to RL is just 0.1. Okay, then 1 point. Let's say 1 to 1 is just 0.1 over 1, right? And if n is 3, then this is 9 plus 0.1. right? So let me calculate that ratio. 1 divided by 1 plus 1 to 1 divided by 9.
99.
98.9네, 그지?
8.9.
So 8, 9, this line. How about this? This is just 1, which is a 0.909, okay? About 8%, right? About 8% improvement, okay? By, increasing the ratio. But we notice that if you increase drastically, right, then it might hurt your performance, right? Because the coupling coefficient will be much, much smaller than 1, which will induce a loss, another loss, right? Because loss is directly related to k square q1, q2, right? This is transformer efficiency. So anyway, there are lots of things to consider. Okay. Okay. So now let's estimate the switching loss. Okay. So we can estimate the switching loss by notice that the on resistor is directly related to GM set. Okay. This is actually this line in this is R on, okay, which is actually 1 over GM, okay. So this is a linear line in triode. But we notice that in order for us to make this equal line, VDS has to be almost 0, or VDS must be much, much smaller than 2V overdrive voltage. If you don't meet this requirement, this is incorrect, okay? So anyway, let's assume, and also we notice that this relation is valid only for long channel device. If it is a short channel device, this is invalid, okay? You also we notice that, okay? Because the GM at short channel device is just what? Mu C, I'm sorry, not mu, which is just a Cox, and W, and what? V set, right? So which is just a directly proportional to this, which is nothing to do with uh, length. Okay. So anyway, we just assume this is a long channel device and operating in triode, and VDS is much, much smaller than 2V overdrive voltage. Okay. So in this case, R1 is just 1 over GM set. So also you know omega t is GM over CGS plus CGD, which can be represented by this, right? Which is exactly what? 1 over RC, which is a time constant, right? Time constant of RC network, okay? This is a very abrupt, modeling, very rough modeling of the, uh, device operation. So the total input power involves the switching approximately 2 CGS plus 2 gamma CGS. Why is that? Because each device has a CGS plus CGD, which is 1 plus gamma CGS, right? So we have a 2, right? Therefore, is right. Okay. So as a upper boundary, right? we just set gamma equal 1. Typically, gamma is 0.6, okay? 0.6, but we just set it to 1, okay? For the simplification, okay? Then what is this? P loss is half of C total VDC scale F, right? So which is actually CGS is just what is that? This is 1, and so this is 4 CGS, right? 4 CGS. 4 CGS multiplied by 2. So this is 2 CGS. Okay? This is 2 CGS VDC scale F. Okay? Uh, so so this CGS can be represented by this line. So this is what? This omega t is R on, and this is 2 CGS. Okay? So 2 CGS is just R on omega t 1, right? So you just put this to here, okay? Then this is 1 over R on omega t and VDC scale F, okay? This is this value, okay? So you need to so you have to remove this, okay? This is correct, right? Because here, 1/2 is neglected, so we have to put 1/2 because of P loss energy, right? Energy loss is calculated by energy stored is calculated by 1/2 CV scale, right? This is energy storage. Or if it is switching, this is energy loss, okay? So the power wise, right? Energy divided by time is power. So energy multiplied by frequency is power. So this is power. Okay. This is power. So you have to put 1/2 here. Okay. So make sense? Okay. The power handling capability of class D is given by here, right? Drain max is 2 VDD if we use the inductor, right? So we use the inductor like this way. We use the inductor here. The half circuit wise is given by this line. So since we use the inductor line, so drain max is 2 VDD. That's what it means. Okay. So I drain max is since we use the 1 to n, right? So NI0, right? So power handling capability, which is PC, is P out divided by 2 V drain max multiplied by I drain max. Okay. So two is we have two devices, right? So that's why we have two. Okay. So P out it was already calculated, right? P out was given by this, right? So if you put them together, right? This value is eta divided by 2 pi, which is around 0.16. Okay. So this is similar to actually class A amplifier. Okay. So many people have implemented a class D amplifier. Actually, people more prefer, inverted class D amplifier to class D amplifier. Okay. So let's talk about class inverted D amplifier. We say this is a class inverted D. Okay, inverted. because this is 1 over d, right? This is inverted. This is very funny, but class E inverted. There is the class E inverted, class F inverted, and class S inverted, class J inverted. What does that mean? The inversion means voltage becomes current. Current becomes voltage. Series resonance becomes a parallel resonance. Okay? This is an inversion. Okay? So the inverted class B, class D amplifier means the scale wave voltage becomes scale wave current. Sinusoidal current becomes a sinusoidal voltage. Okay? Series LRC filter becomes a parallel LRC filter. Okay? Make sense? So this is looking like this. Is this looking uh, quite complex? Actually, no, not at all. So this is actually speak exactly conventional amplifier. Okay, and transformer and another transformer. This line, and we have a resonance circuit like this. That's it. This RL is maybe placed over here. It doesn't matter, right? So if this is N2 1, then effectively here RL N 1 over N square. Okay, so it doesn't matter. So this is exactly this. Okay, it's very nice. Why? Because this capacitance is actually here, naturally here, right? Why? You have a drain source capacitor, right? Drain source two drain source capacitor in common, right? Which is this. Okay, you have a transformer over here, which is this. Okay, so everything is all set. Very good to make a class inverted D amplifier. Okay, so how about scale wave current? It's a very natural. Why? Because as you can see, right, between these two differential pair, right? So if you take a look at voltage, right, over here, right, this voltage is what? This
This
voltage is sinusoidal, right, in AC wise, because this is you know high at omega zero, and for other frequency it becomes low. Okay, so makes sense. The parallel network is looking like this, right? Impedance wise, this right, omega zero, right? So at 2 omega zero or DC, right? This is short,
shoot.
okay? Which means there is no voltage between two, okay? So the output is definitely sinusoidal because of this resonance circuit, okay? So output voltage is sinusoidal, okay? Check. How about scale wave current? Because this is abruptly switching, right? The current is abruptly switched, right? Which is different from previous, right? Previously, the voltage is abrupt, right? The current is conducting through, the current is conducting through this, okay? So current is sinusoidal, but voltage is abrupt, right? Voltage is abrupt. But in this case, right, current is abrupt. Why? Because this switch just directly make it open, right? So since this is open, there is no current conduction. So the current is looking like this, okay? And for the voltage, this is there is a differential voltage only at omega zero, which is this. Okay, make sense? So VS1 is given by this. So 0 to theta is 0 to pi. So the first, conduction, this is 0. And for pi to 2 pi, so it becomes, 4 divided by 4 pi, which is actually, exactly same with the uh, rectangular pulse, right? This is actually sine, 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 sine function, right? Sine function. The first harmonic is 4 divided by 4, right? 4 divided by pi. So which is this? Okay. So that's why you get this. Okay. Uh, any question? This is widely used. Okay. Professor Nina Jad group also presented invert class D amplifiers, and it was highlighted on in the many journal papers. So you guys just take a look at those. Very interesting. Okay. Now let's move to class E amplifier. Okay. So this class E amplifier is also a switching amplifier, but the switching mechanism is a little bit different from class D amplifier. Okay. The beauty of this class E amplifier is that you know uh, this class E amplifier can observe parasitic capacitance into the load network. Okay, this is very good, right? Because previously, different from inverted class D. Of course, inverted class D can observe, but for the class D amplifier, it cannot observe any parasitic capacitor, right? As can be seen here. You know, capacitor is here, and there is another capacitor, which is just hassle, right? So, however, for class E amplifier, you can avoid this problem. Okay. So the load network should be carefully designed to ensure zero switching condition. Okay. Zero switching condition means that there is no overlap between voltage and current. Okay. So the first condition is that M1 sustains a small voltage when it carries current, okay? Which means R1 should be very small. R1 is teeny tiny, okay? This is the first condition. Second condition, R1 carries a small current when it sustains a finite voltage, okay? R1 carries a small current, which means, when output is high, then this has a no current, very small amount of current. Okay, and the third one is the transition time between on and off state are minimized, which means the switching response should be very fast. Otherwise, there should be overlapping region. Okay, hold on a second. Let me go back. Okay. 손이 따가워가지고 내가 이걸 쓰니까 쓰면 안 되거든 내가. 이 자꾸 쓰니까 손에 땀이 차여가지고 진짜 잠깐만. Alright, let's go ahead. 야, 가급적 내가 적진 않을게.
네.
이해 좀 해줘. Okay. So it has to be minimized, which means when it's turn on and off, then this transition has to be very fast. Okay. Otherwise, if this is smoothly going up, right, then definitely there will be overlap region, right? Okay. This is not good, right? Okay. So uh, theoretically, it's something like this. Okay. So we have to deal with finite input and output transition, right? As we've seen before. That is the most critical point for class E amplifier. Okay. So the basic structure of class E amplifier is looking like this. This is actually, you know, uh, the signal shape engineering. Okay, signal shape engineering. So so the gate of output device must be switched as abruptly as possible, right, to maximize the efficiency. However, the larger output transistor typically necessitate the resonance at its gate, right? So, which means the receiving signal must be sinusoidal, right? Because this is a resonance circuit, right? To drive this. Make sense? Okay. So, with this sinusoidal input, right, the output must be not like this, but like smoothly going up and smoothly going out, right? This is the issue, right? Okay. So, how can we deal with this? Okay. So, let's take a look at uh, you know, the first figure. So ID, right? ID is just conducting current, okay? And this is turned off at this point, turned off at this point, okay? Then it's just smoothly going down, and Vx is started to charge. So since it is charging C1 and C2, right? Vx is start to going up. Make sense? All right. So this ID1 has to be small enough when it is charging Vx. Okay, makes sense. In the same way, when this is discharging, right? Discharging. So this is discharging. So Vx is getting small. Then I1 has to be getting higher after a certain amount of time. Also, this has to be flat, which means the derivative of Vx should be flat. Okay, this has to be zero. Okay, this is a zero voltage switching condition, right? Okay, so there are three conditions required for Vx. Okay, so uh, this is the same story. So you guys just read. I already talked about this. So okay, so let me read again. First, as switch turns off, right? Vx remains low long enough for the current to drop to zero. Okay, i.e., Vx and ID have non-overlapping waveform. Okay, so the first condition resolved the issue of a finite fall time at the gate of M1. Okay, the first one is actually this. Okay, so and second one, Vx reaches zero just before switch turns on. Okay, Vx should be zero even before switching turns on. Okay, So you need to have some resonance mechanism, right? Otherwise, you never ever can get this condition, right? How come Vx becomes 0 without switching turns on? It's because class E use the resonance mechanism. Okay, so this second condition ensures that the VDS and ID of switching device do not overlap in the vicinity of turn off point, right? So the top one is turn on point, the top one is turn off point, the bottom one is turn on point. Okay, both conditions should met. Okay, also the third one, this means it has to be flat. Vx should be flat. dv dt is also near zero when switch turns on, something like this, something like this. When switch turns on, ID started to conduct, right? So if it is not zero, then there is overlap, which is reflected as the loss. Okay. So the third condition also lowers the sensitivity of the efficiency to violations of second condition. Right? So uh, turn on point, right? If it is not like this, then with some difference, it will induce large amount of loss, right? So we have to set this dv dt equal to 0. Okay. Also, the time response depends on the Q, quality factor Q of the network and appears as shown below, right? This is underdamping, this is a critical damping, this is a overdamping, right? So we have to choose this, right? So let's take a look at this, okay? When M1 turns on, right, the circuit's voltage and current are described as below, right? So when M1 turns on, it shorts X to ground, but carries a little current at the beginning, right? Because this is abruptly changing, right? And abruptly changing, and with this, already the current is conducted through here. So Vx becomes already near to 0. Okay, we have this, right? For the class D, we don't have this, right? So this is a very, very good circuit mechanism, right? Because this can be included. This can part of this can be parasitic CGS of the device, right? So this make the uh, the non-overlapping of ID and Vx when M1 turns on. Okay, so if M R1 is small, right, then Vx remains near zero because conduction current is already small, right? So the LD sustains a relatively constant voltage because this is almost zero, right? So the voltage is just VDD minus Vx, which is almost zero. And this is omega LT, which is a T divided by LD, right? This is the same as omega L, 1 over omega, 1 over omega LD, right? Make sense? Okay.
Yeah.
So from this relation, you can calculate the ID, which is almost constant. Okay. So in half a circle with a M1 turns off, previously was a M1 turns on, right? The voltage and currents are plotted as below. Okay. So as can be seen, right? So since this is turned off at this point, Vx started to charge, right? So Vx started to increase at certain point, and because this is second order resonance circuit, right? So there should be, decrease again through this C1, okay? C1 is there, right? So anyway, once you charge and then this will discharge through C1. So it is looking like this. Okay. How about ILD? ILD is when this is on, Vx is almost zero. Therefore, there is a constant ILD. ILD is gradually increased as time goes by. And once this is switched off, then there is no current through this. So current is reduced, started to reduce. Okay. So how about Vout? Vout is this signal is actually a root signal, which is a half sine, right? Which has an abundant number of harmonics. And once it passes through this C2L1, this is a series, network, then you will get, fundamental up. Okay, so you get this sinusoidal signal, right? So as can be seen, the basic mechanism is something like this. This is LD, and this is a LCC, and this is a resistor, and of course the series bandpass network is here, so just omitted. At resonance frequency, it is a short line. It's almost a short line. So it is exactly like uh, parallel network. So the quality factor Q is given by R square root of C divided by L for this parallel network. Okay. So once Q is given by this, you have to choose Q such a way that the voltage at this Vx, okay, this Vx should be something like this, half sine, okay, half sine. When it is crossed, then this is gone away, right? So the perfect Q is should looking like this, okay? It's like overdamping, but touches the zero at this point, okay? Then it becomes perfectly half sine. Make sense? 알겠지?
네, 교수님.
이거를 Q를 조절을 해서 여러분들이 여기를
지-
텐전 시뮬레이션에서 봐. 보면 이렇게 될 거 아니야. 이렇게 여기를 터치하는 이 Q를 찾아야 돼.
네,
그러면 이거는 나중에 어떻게 돼? 이거는 지금 이게 셔터 딱 스위치 오프 되면 스위치 온 되면 이거 다 없어질 거 아니야, 이거는. 그러니까 이렇게 된다고. 이렇게. 스위치 오픈 크로스 이렇게. 알겠지? 그럼
네,
어떻게 돼? I I하고 C하고 완전히 그냥 따로잖아, 이렇게. I하고 V하고. 그지? 그러면 어떻게 돼? 하나도 겹치는 게 없으니까. 어? Therefore, you can get almost 100% of efficiency. Okay? So output power of class E is, however, output power of class E is very low. Previously, right, class A amplifier is a 0.125. Class D amplifier is a 0.16, right? 0.16, right? So the capability of class E amplifier, the main problem of this class E amplifier is this, okay? This low power handling capability, okay? For example, if Vmax is 8 volt, right? At 50 ohm, Vout is only less than 60 milliwatt, okay? Which means you need to use, large transformation ratio, right? Okay, so here are issues in class E amplifier, okay? So the problems with the class E amplifier include low power gain. Actually, the power gain is looking weird concept for the switching amplifier, right? But anyway, it has a low power gain because the swing itself is small. And the large voltage swing, right? It includes a low power gain and large voltage swing. And drain waveform can swing to more than 3.5 times the supply voltage, which is very, very bad for the CMOS amplifier, right? Right. So, however, I think if we implement class E in certain point of time, maybe we can achieve a good performance for gallium nitride. Okay, so this is another thing that we need to consider. Okay, however, the power capacity is very very low. This is a point, not colon. Okay, this is point. This is point. Okay, this is just a point one, right? Point one. Much. However, it is still much better than class C. Okay, class C is a 0.08 something. Okay, depending on the setup. Okay, conduction angle. Right. So this is a class D, class E power amplifier example, which was presented by Patrick Renard when he was a student, I think. Uh, Michel Steyart must be his advisor. Okay, so anyway, Patrick Renard, published this, and it has an efficiency of 40%. Total efficiency is 34%. Okay, and the last one, and there is another very well designed class E amplifier from Berkeley. So I don't know his name, I forgot, but he's a student of Professor Gray, and the result was quite amazing at that time. It was published early, 2000, early of 2000. Okay, so if you are interested in, then just take a look at. Of course, it is one of the homework. Okay, you guys anyway need to search. Okay, so wanna see what's going on, right? Let's talk about class F. Okay, so this class F amplifier is actually not the switching amplifier. Okay, so exactly speaking, in the generic switching stage, the load network provide a high termination impedance as third harmonic, right? The voltage waveform across the switch exhibit sharper edge than sinusoidal, thereby reducing the power loss in the transistor, right? Which means what it means is that this is just generating sinusoidal. Okay, this is sinusoidal from the transconductance. However, since it has some network which is actually open at 3 omega 0. Okay, the third harmonic component is has a high impedance, which means at this vx, right, this is sine omega t plus a sine 3 omega t, which make this VC shape close to close to close to rectangle. Make sense? So once we add up so the harmonics, right? For example, if you want to make it more rectangular shape, then you just add another parallel network operating at fifth omega zero. Okay, then it will be more like a rectangle. Why do you want a rectangle shape? Because if you keep this rectangle, right, it becomes close to class E or class D, which is a switching amplifier, right? Which do not overlap each other. Make sense?
Yes.
Okay, so using this very simple mechanism, right? It is very interesting that class F amplifier can be easily implemented from class D amplifier, class B amplifier, plus 3 omega 0 parallel network. Then it becomes class F. Okay? Very interesting, right? So if you really want to implement, high efficiency with a simplest, approach, then you just implement. You just add up this parallel network in series with your load, then it's done. Okay, 10% of improvement. Great, right? Make sense? Okay, here is a very smart way of achieving this approach. Okay, what if we just implement something like this? Okay, this is an inverter, right? Impedance inverter. Since this is the impedance inverter, right? What is operating? Let's say this is operating omega zero, right? At omega zero, what is this? This is a parallel network, right? Parallel network. Okay. So this is a lambda of 4. Okay. So which means uh, this is if you just implement this is a low impedance, this becomes a high impedance, right? So at 3 omega 0, right? Is this a high or low? This is a low, right?
Low.
Something like this, right? This is the main characteristic of your parallel network, right? So at 3 omega 0, right? This must be very low. Make sense? What happened to this? What happened to this point? Since this is a
High.
lambda of 4 at omega 0, right? What is that? At 3 omega 0, right? This becomes 3 lambda over 4, which is the same as lambda of 4. Make sense? This is still work as an inverter at pseudo 3 omega 0, right? Pseudo harmonics. Therefore, since this is a low as pseudo harmonic, this must be high. So it must be looking like this. Make sense? The VS, okay? Make sense? How about second harmonics? Second harmonics becomes means this is a 2 lambda 0, right? A second harmonics, right? A second harmonics. Effectively, this is a half lambda, right? So it doesn't make it, if this is a low at 2 omega 0, this impedance is also low. Therefore, it does not adopt any even harmonics, right? That's great. So theoretically, it can prohibit or boost all the harmonics at this point. Okay? Boost all the harmonics at this point, which means the signal becomes almost rectangular with just such a simple approach. Okay? Great. Right? What's the problem of this? What's the problem of this? It will be very lossy, right? Look at this. This is lambda over 4. Very lengthy. Okay? In CMOS, this must be almost 1 dB of loss. Okay? You need to compare, right? The advantage and disadvantage, right? What you get is a 10% of efficiency improvement. However, you will lose about 10% of loss from this itself. Okay? So you have to compromise, right, in the design. Okay? But gallium nitride, I think it still may work because gallium nitride has a very wide band, very wide, transmission line, right? Which means loss must be much smaller than CMOS technology. So I think if area is allowed, then we can just improve the efficiency by using this approach. Okay, it is designed to be done in certain, in certain time in the future. Okay, not this time, but near future. Okay. Once we completed all the conventional design, then I want to approach it with a different type of amplifier. That's my plan. That's why I teach this. Okay. All right. Let's talk about cascode output stage. All right. So this is what we've done. Right. So we just add up cascode stage. Okay. What's the good thing and better thing about this? Good thing is, by adding up this, right, even though this has a limited breakdown voltage, we can sustain much higher voltage swing, right? What is better thing? Better thing is the swing is limited, right? The swing is quite limited, right? For example, uh, let's say this swing is this, right? Let's say this swing is, for example, V in, V bias, and this is a V peak, V bias plus V peak in, right? Then this voltage should be, VB should not higher than this, right? VP in minus V threshold. Otherwise, this becomes in trial, right? We don't want that, right? So the swing must be very limited, right? This swing is also, you know, limited by this VB, right? So uh, let's take a look at step by step, okay? So also the good thing about Cascode is this Cascode device is a shield. It's a M1, right? So because this M1 VDS, VDS of M1 is always less than VB minus V threshold 2, right? Because this has to be turned on, right, to conduct the current, which means this voltage is at best, VB minus V threshold. It cannot be higher than this, right? Which means this is safe, right? Make sense? Okay. 야, 너들 이해했냐?
Yes.
민규는 너 이해했어? 어?
네, 그 실드 해주는
그러니까 왜,
이해했습니다.
왜, 왜, 왜 그렇지? 간단하게 한번 설명해봐.
M2가 켜지려면은 VY가 VB 마이너스
그렇지.
VTH로 고정하는 거.
그렇지. 항상 그 이하가 되면 안 되지, 그지? 그
네,
이상이 되면
맞습니다.
안 되지, 그지?
네,
그 이상이
맞습니다.
되면은 얘가 꺼지잖아. 그러니까 켜진다는 거는 얘가 at best it should be just a VB minus V threshold, right? Okay. Good. All right. So this is let's determine the maximum terminal to terminal voltage difference of M1, okay, and M2 in cascade stage, right? Assume V in has a peak voltage of V0, okay, and DC level of Vm, okay, and Vx has a peak amplitude of Vx as a peak amplitude of Vp, and DC level is definitely VDD, right? Then very straightforward, right? So initially, let's take a look at uh, V drain source 2, right? Since this is what? This is a VB, right? So in order for this to be turned on, this has to be VB minus V threshold 2, okay? And what is this? This is a VDD plus the peak is what? VP, right? VP, right? So the maximum difference must be VDD plus VP minus VB minus V threshold 2. Make sense? Okay, so this is maximum VDS. Okay, in this case, what is a VDG? What is VDG? Difference between this and this, right? So since this is a what? VDD plus VP, right? And this is VB, right? So the difference is this. Okay. Uh, How about transfer M1? Okay, M1 is I already mentioned, right? So this is a V out, right? So this is a VM plus V out, right? And also this is a VB minus V threshold 2, right? So VDG is a VB minus V threshold 2 minus VM plus V out. Okay. Uh, oh, no, no, no. So the maximum value of VDG, right? Maximum value of VDG, which means this has to be lowest value. So this, right? The maximum value of VDG is VB1 minus V threshold. This is a fixed minus the small value of V in, which is VM minus V out, right? Make sense? Make sense? That's one. Okay. How about VDS1? This is a V threshold, VB minus V threshold, right? V threshold 2. Okay. That's it. Okay. So for the linearity, right, we can compare for the linearity wise, right? Cascode has inferior performance compared with the common source amplifier. So as can be seen here, right? So the swing is limited by VP cast, right? This VP cast is caused by caused by this, right? So VP cast is actually uh, you know uh, what is that? A what is A from A가 어디지? 이거 안 보자 이게 뭔가? VDD minus VP cast, right? VDD minus VP cast. VDD minus VP cast is this, right? And VDS 이게 A고 이게 B인갑다. 그지? 그래서 지금 if you take a look at this, then VDD this right this point, right? This point has to be VM plus V out plus V threshold 1, right? Should meet this, right? This is a VDD minus VP cast. This is our expected largest swing. And this is this swing over here. And this is VDS2, right? This is this point, right? This point should be, larger than this, right? So, therefore, VM plus V out, this is the peak, input peak is VDD minus VP cast minus VDS minus V threshold 1, okay? This is that, okay? All right, and for B, right, same. So VDD minus VPCS at this point, right? And this is V out plus VM plus V threshold, V out plus V threshold 1 plus VM equals V threshold 1. No. equals what? Equals this, right? Vx, right? Vx, which is VDD minus VP CS. Okay? So you compare. Therefore, V out plus Vm equals VDD minus Vp cascade CS minus V threshold 1. Okay? If you compare this with this, okay, then VPCS is actually VP cas plus VDS2, which means VP cas has a smaller amount of swing by this amount, VPCS minus VDS2. Okay, this amount of VDS2 will be here. Okay, so this VDS swing, this amount will be VDS2. Okay, so you have a two VDS. You have a two VDS of swing, VDS2 of swing, loss in the output if you use cascade, right? But this is valid only for linear amplifier, okay? If you use a switch mode amplifier, it doesn't matter, okay? This is just a stability of cascade stage. It doesn't make any, important observation. What it mentioned is that if this is a negative impedance, right? Then this G out has to be larger than this to compensate the loss. So real value of this plus this has to be larger than zero, right? Okay. So how about parallel network? So if you take a look at this parallel network, right? So this RP is in parallel, right? This is RP, okay? And this is another R in, okay? So this is in parallel. So for the parallel network, right? If RP is small, which means it has more vulnerable to the oscillation. If RP is large, then it's easy to make it stabilized, okay? Which means, we need to, if RP is small, if we set RP equal R in, right? If R in is oscillating, then RP has to be smaller than R in, okay? But in Rajavi's book, it was the opposite, okay? So just be careful on this. 이해했냐, 뭔 말인지? 어? 이게 패러럴 네트워크일 때는 이게, 패러럴 네트워크로 여러분들 봤을 때 패러럴 네트워크의 퍼포먼스를 보려면 여기에 임피던스가 작은 게 더 네거티브 임피던스 영향이 크냐, 큰 게 임피던스, 네거티브 임피던스 영향이 크냐. 이거는 작으면 작을수록 이게 있는 오실레이션 한다는 이야기야. 그지? 그리고 여기서 보이는 게 작아. 얘가 패러렐로 작아. 그럼 여기는 얘보다 더 작아야 돼, 그지? 패러렐
네.
네트워크, 그지? 안 그럼 발진할 거 아니야, 그지? 그 말이야, 그 말. 어? 여기 가정은 R인이 마이너스는 가능했을 때 이건 뭐 별것도 아닌데 얘 그러니까 지가 또 잘못해놨어. 자, large signal impedance matching. So the impedance matching is a very, linear transformation, right? So basically, for the amplifier, right, this is typically, the make a RL to lower impedance, right? We just want to make a RL to lower impedance. That's the design objective of matching network, right? Right. But in practice, right, those C and R are actually a function of output power. So we cannot directly, take out gamma out and convert it to G out and use this in designing matching network. It's impossible, right? Instead, we use, since this is a nonlinear complex, network system, we have to use load pool, right? We have to use load pool, right? So let's observe, what's going on in terms of, transformation ratio. I mean, transformation, okay? So this is the simple, structure of a common source amplifier, right? Let's say we have a, drain to bulk capacitor here, and CL is here, right? And let's say we implement, uh, the matching network here, okay? So, so here PRL is defined as a power delivered to the load, right? Okay, and uh, PRO1 is power consumed by M1. Okay, so it's very straightforward, right? So for this architecture, right, power delivered to the load is just generated current GMVGS multiplied by, this is division ratio, right? RO plus RL and RO. This is current, right? And current scale multiplied by RL, right? That is actually, the power delivered to here, right? Since this is let's say this VGS is a peak power, then this has to be 1/2. Okay. So this is this. Okay. Here IP is what? GM VGS. Okay. All right. How about PRO? Same, right? You just provide half of IP scale and RO plus RL and RL, right? And just take RO, right? This, right? Okay. That's what we get here. Right? Okay. Make sense? So for the maximum power transfer, right, we definitely understand that RO has to be RL, right? RO1 has to be RL. In this condition, right, we meet this requirement. What is this? P delivered to load divided by P delivered to consumed by, your device is a ratio RO1 divided by RL, which means your RL should be reduced. RL should be reduced to minimize, to boost the efficiency, right? This is efficiency, right? You have to reduce RL. How? You just add up matching network to make it lower. Okay. So as I mentioned before, right, this power amplifier in hard switching mode is a very nonlinear system. Therefore, we cannot use a linear model, right? So we have to use a load pool measurement. The load pool is very simple, right? We just put given input power and set this output power as a P1 and just tune this tuner, okay? And make this P out constant, okay? So by changing tuner impedance, we keep output voltage, output power same, okay? We draw, okay? This is good. So once we change this to P out plus 1 dB more, we draw again, 1 dB more, draw again, it doesn't change, then this is optimal, okay? This is how we get the load pool, okay? So load is just pulled by using tuner, that's it. For this input line, we also have a tuner such a way that the maximum power delivered is guaranteed by controlling this source, okay? So we just, assume that this input power is kept constant, okay? Because this is natural, right? Because if this is a hard switching, right, the impedance at this point is also changing. So we use a tuner to keep this P in constant. Okay? Make sense? 대답을 안 해. 뭐가 좋겠니? 이해했냐?
네.
Okay. So now let's take a look at basic linearization technique. The first one is a feed-forward mechanism. Okay, the feed-forward architecture computes the error and with a proper scaling, subtract it from the output waveform. Okay, that's a basic, feedback, similar to feedback network, right? But this is not feedback, right? The output is not fed back, right? This is just a feed forward. So the input is right. Input is two paths. I mean, this is path one. This is path two. Okay. So we just subtract. Okay. Subtract and amplifier again, and just add up. Then once this is subtracted line with this input line, there exists distorted factor here, and this is subtracted from the output. Then this becomes linearized. Okay, this is a widely used one, right? Okay. The feeder forward, however, the feeder forward suffers from several shortcomings, right? First, the analog delay element, right? Those analog delay. This is a real implementation because there is a delay, right, in the path of a signal. So this there is also delay in the path of signal, right? Those delay element introduce loss. Okay, and also the loss of alpha subtract line is degrade efficiency. Okay, this is after amplifier degrade seriously. The linearity improvement depends on the gain and phase matching of the signal censored by each subtract. Right. What it means is that what if this is inverted, right? Then it doesn't work. So it must be well controlled. The phase and gain must be well controlled to subtract correctly. Okay. This is an example of addition of signal in current domain and feed forward. So thing is that a student just insists that the output subtraction need not introduce loss if it is performed in current domain, right? If it is in current domain, the current uh, uh, but the result is no, it's not practical. Why? Because you know the main power amplifier is followed by delay line, right? And the performing delay in the current mode is very difficult. No way of making delay. If it is voltage, then you may just use RC network, but if current, then there is no good way. So definitely, to achieve, delay, it has to be in voltage mode. Okay, so anyway, it's impossible because of leakage of time delay in current mode. Okay, so consider the system in previous slide as core PA. Apply another level of feed forward to further improve the linearity. There are just make a two stage linearization. Okay, the first stage is same, just take this and just scale down and add up, and if there is a distortion, right, then distortion is amplified again, and to meet the phase between this and this, right, and it just a subtract. So okay, that's fine. So let's do it again. Just take V into and just rescale and subtract again and amplify again, right? Do it two times, right? And this AV prime must be actually, let's say this is a, yeah, okay. This AV prime must be almost similar to this, right? Okay, just a tweet again, okay? Uh, that's it. But, you know, what is the problem with this? It consumes more power,
Power consumption.
yeah, and more complex, okay? So this is a very interesting example of feeder forward system, right? So as we were seeing, as we were observed, right, the switching mode power amplifier is completely nonlinear, right? So its output transistor operates as a switch. Since it's an operating switch, right, the output must be just a fixed, like this way, right? No AM amplitude information at all at the output, right? So that's why we use, switch mode power amplifier only for PSK, MPSK, okay? But we're gonna learn, polar modulation next, lecture, which will be the last lecture, okay? So in this class, and you guys, after that class, 2 weeks later, you guys have to present your work, okay? That's a final exam. Okay? I will evaluate very seriously, okay? You notice, okay? Don't get disappointed if you get bad grade, okay? That's your work, all right? So 2 weeks later, right? Okay, keep in mind. And also send me all the homework that you've done up until next week, okay? Just compress it, zip it to single file of each student and send it to me, okay? I will I will evaluate. If you miss something, then just fill them in all, okay? You have to complete, right? I will evaluate them as a midterm exam, okay? Right? Any question? Okay, let me go back to here. Okay. So this is a very interesting dialect. Okay, so let's say the output transistor acting as an idle switch. Okay, then the power amplifier removes the envelope of signal, right? So retaining only phase modulation. Okay, so if V in is a V envelope cosine omega t plus pi t, then output must be this, right? At this point, Vm. V0 cosine omega 0 t plus pi t. Pi t is resolved, but V envelope is distorted to V0, right? All right. So what happened to feed forward system? Okay. Let's say there is a, signal, AM signal at the amplitude, right? And of course, it's a very how to define the voltage gain, right? But anyway, let's say this is AV, okay? I also don't know what that means, okay? How do I consider voltage gain from here to here? Or do I consider the voltage gain from here to here? No one knows, right? Right? Makes sense? It
Yeah.
doesn't make any sense, right? For anyway, Razavi just give an example like this. This is very interesting, okay? Anyway, let's say there is a AV, maybe average the value. Let's say this V in average over, V out over V in average. Okay. Let me say this is AV. Okay. Whatever it is, just choose one reference. Okay. So what is a VP here? Just subtract between these two. This is scaled down by AV, which is defined by this. Okay. Whatever it is, this is a constant, right? So V n this, right, minus V in is VP. So Vn is V out divided by AV. Okay, so you get this. Okay, then V out is what? V out is VP multiplied by AV, right? VP multiplied by AV is AV, right? AV. Then this is VQ, okay? This is VQ, which is just multiplied by AV, which becomes V0 minus AV V envelope cosine omega. Make sense? Okay. What is output? This is V0 cosine omega t plus pi, right? If you subtract them, what is left is this. Oh, good. You resolve output power. Okay, that's good, right? So conceptually speaking, even though you are using switch mode power amplifier, eventually you can resolve your information in the envelope, right? It's a very looking nice, but it's a natural, right? It's natural. Look at this. You just amplify your input throughout this. This is constant, right? What is that? Does it make sense? No, it doesn't make any sense to me. Does it make sense to you guys? 야, 이게 의미가 있냐, 이게? 어? 의미가 있냐?
없습니다.
의미가 없어, 이건. 어? 알겠지? 그냥 중포한 거 아니야, 중포. 그냥 위로 중포한 거 아니니까. 어? 그치?
그냥
맞습니다.
신호 증폭한.
Alright. Anyway, therefore, you guys need to understand what's going on behind the surface, okay? So this is a Cartesian feedback. So if a power amplifier output is not converted and compared with the baseband signal, an error term proportional to non-linearity of transmitter chain can be created. Okay, it's the same as before. Okay, with a quadrature down conversion, right? This is called as a Cartesian feedback. Okay, Cartesian feedback use INQ, right, to preserve the phase information. Okay, Cartesian feedback avoids the output subtract and is much less sensitive to path mismatch, but requires some linearity in power amplifier. Also requires a very good INQ. Okay, so let's take a look at this. So here you have a two mixer, right? One is let's say this input is coming, and this is MX up converted to with a sine omega L, right? So this is RF, okay, and amplified, and the output is down converted with this, okay, and through the low pass filter and compare with this. So this VF should attract V in, right? VF should attract V in. So once this VF is the same with the V in, then which means that there is no error at all. Okay. So here is the implementation. So you have a I signal and Q signal, which conserve the phase information, and just take a part of a power amplifier signal and just shift the arrow quadrature phase like this, because of there is a phase term theta. So we just put them this together and just compare. Okay, this is a negative feedback. So since we use I and Q, this is a Cartesian feedback. Okay, and there is another way of making things linearization, things linearized. So it's called as a predistortion. So if power amplifier nonlinearity is well understood, then we can predistort the input waveform, right? So it's very simple approach, right? So let's say this is a distorted, right? Like this. Typically, the distortion is caused by ax plus a1, a2 x squared plus a3 x third, right? This term, right? This term a1, a3 is less than 0, which means the polarity between these two are different, right? So if you rearrange it, this, then the a1 part becomes a1 plus a3, uh, a1 plus a3 and x, something like this, right? So this will, as input power increase, this will be more drastic, right? So let's say this is so therefore, it becomes distort, it becomes reduced because this is a negative. If this is positive, if this is negative, this is positive. Therefore, in magnitude wise, it's just saturated due to this nonlinearity. Okay, since we know this, what if we just make an inversion using this y equal x with respect to y equal x, we just make an inverted uh, you know the function, inversion function, right? Just to make inversion function, output is linearized. So there are three drawbacks. So the first one is if power nonlinearity varies with the process temperature and load impedance, then the output is not good, right? The second one is if there exists absolute nonlinearity, right? So it cannot, you know, correct. It cannot correct this absolute nonlinearity, right? Third one is, antenna impedance. If antenna impedance is varying, right, then it will affect power amplifier performance, right? But this distortion mechanism does not, you know, take into account of that, right? That's the problem of pre-distortion, right? So this is the example of pre-distortion with the feedback. So uh, the feedback, you know, actually this is a Cartesian feedback. Same with the Cartesian feedback, right? We just you know pre-distorter. There is pre-distorter, right? For the pre-distorter, there is no feedback path, right? But if you just use this feedback and convert it to that, this is Cartesian. Same, right? Same as before. This is an analog way of doing. This is a digital way of doing. No difference. Okay. Uh, this is another one, which is envelope feedback. Okay, so to reduce the envelope nonlinearity, right? Let's say if there happens a AM to AM conversion, right? So we need to practice by using this envelope feedback. Okay, so here is the way. So there are two envelope detector. One is at the input, so it catch the level of input, and the same, right? Same as before. And this is a variable gain amplifier, and just get the part of output and detect the level and compare two level and change the gain to drive this level. Okay, same same as before, just for the AM to AM distortion to reduce the AM to AM distortion. Okay, so how does distortion of embedded detector affect the performance of our system? No affection, no, there is no effect at all. Why? In case envelope detector 1 and envelope detector 2 have exactly same characteristic, right? This is the only difference, right? This is a common mode, right? So there is no effect at all. Okay, makes sense. This is a very good, way of correcting the AM to AM conversion. So let's take a look at this. Okay, so this is a way of developing envelope detection, right? Envelope detection is nothing but the self-mixing, right? Just put input at the IF and input at the arrow, right? It just mix together, then which will generate scale term, right? Scale term, and this is gone with the low pass filter, and you only have this term, right? So which means that this is the output is proportional to scale of your envelope. Okay, this is scale detector. Okay, so source power also can be used as an envelope detector, right? So there is envelope information with the signal carrier, right? So what if we just make a C very large, then this is just a low pass filter, right? Low pass filter. This is 1/GM. So the output is just it's a 1/GM plus SC and SC, right? Which make this as just 1 plus SCGM and 1. This is low pass filter, right? So you have a low pass filter which just take out this high signal and just take out this signal envelope only. Okay, so this track. Okay, here is another way of doing more elegant way of doing. Okay, so previously the output was a scale, right? But I don't want to have a scale. I just want to get the envelope as it is. Okay, so how can I do that? So I just put the limit over here, right? Then I just put V in, and this is a beta V envelope and cosine omega t plus pi t, and this output is V out. So this is a beta V out V in envelope, right? Cosine scale. This cosine scale term is this, right? So it becomes a beta V0 V envelope, which is a V, which means a V out is directly proportional to V envelope. Okay, right? So, but in order for us to make this V out rectangle, right, which is just something like a 0 and V out, right? So we need to cascade the signal. I mean, we need to amplify to make this, you know, go rail to rail, right? This is a VDD and 0. This is typically what we've done in our lab, actually. Okay, we just use limit is very easy to implement. Okay, you may just use this way of, you know, uh, just to use those, let's say, 4. And to make this work at class A, just attach like this way. Okay, then you can nicely make a limiter. Let's say this is sinusoidal and the output is rail to rail. Why? Because the gain of this is what? GMN plus GMP and GDS1 plus GDS2, which is this is a 1, 1, this is 2, okay? And multiply by 1, 2, 3, 4, 4 times. Power over 4, okay? This gain must be very large, right? Therefore, small amount of change will induce swing, rail, rail to VDD. Small amount of change to 0 will rail to 0, okay? So it becomes like this, which is, yeah. Make sense? So as a result, right? As a result, this is very simple, right? Just implement this multiple number of this cascaded. Yeah. Just put to this arrow, okay? Then done, okay? So this is proportional to beta, V envelope, and VDD, and that's it, okay? So this makes sense?
Yeah.
All right,
Yeah.
here is the homework. So you guys need to search papers for class D, E, F, okay? And power amplifiers using envelope feedback and expand, okay? Each student should choose different architecture, discuss each other, okay? It should not be the same, okay? For example, Taewon just choose class E, Mingkyun choose class D, and Sunyeok choose class F, and Dogan choose class maybe uh, inverted class D, right?
Yes.
Bampu just choose PA using envelope feedback, whatever, okay? So you guys choose different, you know, uh, topic, okay? So each student should choose a different architecture PA and present each comparison table and mechanism using PowerPoint, okay? It's 15 minutes of slide, 15 minutes of presentation with 20 pages, okay? Due is before next lecture, okay? So send me slide with 20 pages. Any question? Any question? If this is a little bit, uh, too hasty, then how about next Thursday? 다음 주 목요일로 때로.
아, 네, 알겠습니다.
그게 낫게 어차피 태훈이도 이제 지금 테이프아웃 한다고 태훈이만 힘들지 지금 그지? 다른 사람 좀 힘들긴 건데 다른 애들은 이제 테이프아웃이 물건 나가가지고 순혁이는 순혁이 열심히 하냐 지금? 아 어쨌든 목요일 날 하자. 너들 부담되니까. 다음
네,
주고.
알겠습니다. 네, 알겠습니다.
알겠습니다.
그래. 오케이, alright. Let's wrap it up. Okay. Any question?
네, 그럼 그 과제 취합한 것도 다음 주 목요일까지 보내드리면
다음 주.
아,
다음 주 월요일. 아주 취하고 다음 주.
네, 알겠습니다.
왜냐면 다음 주 내가 마지막 프레젠테이션을 하고 오자.
네.
그 다음 주가 lecture 15이야. 그지? lecture 15에 이건 lecture 10이라고 된 13이잖아 오늘이. 다음 주가 lecture 14고 그 다음 주가 lecture 15인데 그때 너들 발표하는 거야. 프로젝트.
네, 알겠습니다.
이제 뭐 지금 하고 있잖아 너들 다. 각각 하고 있잖아. 발표하면. 그때까지 홈워크까지 나한테 주면 내가 이벨리에이션을 다시 해가지고 중간고사, 기말고사 점수 줍니다. 오케이?
네, 알겠습니다.
네, 알겠습니다.
그래. 수고했어요.
교수님,
어.
이번 주 목요일이 현충일이라 빨간 날인데 세미나는 언제 적을 수 있어요?
수요일 날 하지 뭐 수요일.
알겠습니다.
수요일 날 잠깐 하자. 잠깐. 목요일 날 뭐 계속 일해야 될 것 같아. 수고했어요.
네, 교수님. 네.
감사합니다.
그래. 순혁아,
네, 교수님.
그 윤리 서약서는 이제 뭐 괜찮은 거야? 내가 그냥
제-
뭐 하고 그래?
제출했습니다.
그래?